Chapter 4 Cryptographers Toolbox. This chapter covers the rating system used for ciphers, substitution ciphers, transposition ciphers, fractionation, breaking letters into smaller units, pseudo-random number generators. Secret key ciphers are built from a few basic elements. You can think of these as the tools of the trade. To build a strong cipher, you want all of these tools in your toolbox. That does not mean you should use every element in every cipher. That could lead to excess complexity without any improvement in security. Your cipher would be slower with no added benefit. This chapter covers substitution, transposition, fractionation, and random numbers. I introduce other tools such as text compression in Chapter 10 and blockchaining in Chapter 11. Before discussing the elements, let's talk about strength. The strength of a cipher is measured in bits. Each bit represents one binary choice. If there were a cipher where each ciphertext could represent just one of two possible plain texts, then that cipher would have a strength of 1 bit. For example, 0 equals we lost, 1 equals we won. The size of the key is a limiting factor in determining the strength of a cipher. If a cipher uses 64-bit keys, then its strength can be no more than 64 bits, but the strength can be less if the cipher is weak. Section 4.1 Rating System. In order to give you a general feel for the strengths of the ciphers described in this book, I rate ciphers on a 1 to 10 scale. These are my personal ratings based on my experience and my analysis of how much effort is required to break the cipher using the best techniques I know, and how the ciphers compare to one another and to historical ciphers that were or were not broken in practice. I give much of the analysis in the section preceding each rating. 1 indicates a cipher that can be broken by a beginner with no training, using only paper and pencil and moderate effort. 2 indicates a cipher that can be broken by an experienced amateur or hobbyist, using only paper and pencil. 3 is a cipher that a skilled amateur cryptographer can breach with hand methods. 4 or 5 means that a computer, a trained cryptographer, or both are needed. From 6 to 9 indicates how much computing power an expert opponent would need. 10 denotes a cipher that will stand up against a national cryptographic agency with legions of trained cryptographers using today's largest supercomputers. Sometimes I go outside the scale. 0 means that the cipher can be understood without needing paper or pencil, such as Pig Latin, or this statement. An 11 rating means that the cipher will stand up to potential future ultracomputers far stronger than quantum computers or supercomputers as we currently conceive them. By seeing how I rate different ciphers, you can get the gist of how to rate ciphers that you see elsewhere or that you may invent yourself. Each rating is only an estimate, not a guarantee of strength. The guarantee comes from performing the analyses described in Chapter 12. Section 4.2 Substitution. The first tool in the cryptographer's toolbox is substitution. One unit is substituted for another unit in a text. The plain text units can be single letters, pairs of letters, or longer blocks. The ciphertext units can be letters, blocks of digits, or letter-digit combinations. When all units are single letters, the cipher is called simple substitution, or monoalphabetic. In computer cryptography, the units can be bits, bytes, or blocks of bits or bytes of any length. This section gives a quick glimpse. There is a full discussion in Chapters 5 and 6. One of the oldest known substitution ciphers is the Caesar cipher, used and possibly invented by Julius Caesar, where each letter of the alphabet is replaced by the letter 3 positions later. In modern use, this may be any fixed number of positions earlier or later. The Caesar cipher is rated 1. There is no requirement that all plain text units have the same length. Suppose that the cipher takes letters of the alphabet and substitutes two-digit pairs. There are only 26 letters of the alphabet, but 100 possible digit pairs. This means there are 74 extra pairs the cryptographer can use for some other purpose. One approach, which has been used for hundreds of years, is to provide substitutes for common letter pairs such as TH, ER, ON, AS, and NT, and possibly short words like the and, in addition to the single letters. The plain text units would then be 1, 2, or 3 letters long. This makes the frequencies of the digit pairs more uniform. Since differences in letter frequencies can be used for solving ciphers, making the frequencies more uniform makes the cipher stronger. Another approach is to use the extra pairs to provide additional substitutes for some common letters. This is called homophonic substitution. For example, you might provide 10 substitutes for E, 8 substitutes for T, and so forth. The multiple substitutes for a given letter are called homophones. This is analogous to the way the homophones F and PH both represent the same sound in English. Providing multiple substitutes makes the frequencies of the 100 digit pairs more even. Naturally, both approaches, letter pairs and homophonic substitution, can be combined to get even more uniform frequencies for the digit pairs. In other words, these methods prevent an opponent from using frequency analysis. Section 4.2.1 Huffman codes. In a computer context, the ciphertext units can be strings of bits. A good example is Huffman coding, developed by David A. Huffman in 1952 when he was a student at MIT. I won't cover the method for optimizing the set of codes. I will just give the general concept as an example of a variable length binary code. In Huffman coding, the most frequent letters get short codes, while rarer letters get long codes, based on an underlying letter frequency table. Consequently, fewer bits are required to express the message. This is called text compression. There are even stronger methods for text compression in section 10.7. The most frequent letters in English are E and T, which each occur about 1/8 of the time. Since 8 equals 2 to the power 3, we use 3 bits to represent E and T. We can arbitrarily choose any 3-bit values, say E equals 100 and T equals 111. I call this method mixed Huffman. The next most frequent are A, O, I, N, S, R, H. These occur roughly 1/16 of the time, so we use 4 bits for each of them. We can use any 4-bit codes, except codes starting with 100 or 111, which have already been used. The next group of letters are D, L, U, C, M, F, Y, which each occur about 1/32 of the time, so 5-bit codes are needed, and so forth. Here is a set of mixed Huffman codes I created based on counts of 150,000 letters of English text. Other languages vary. Huffman codes have the prefix property, namely, no code is a prefix of any longer code. For instance, if ABCD is a code, then ABCDE could not also be a code for any choice of binary digits ABCDE. The prefix property was first described by mathematician Émile Léon Post in 1920. Using these code groups, the word style could be encoded as 0110 111 11011 01000 100. Rewriting this in groups of 4 bits gives 0110 1111 1011 0100 0100, which is hexadecimal 6FB44. Although it is nearly impossible for Emily, Sandra's enemy, to identify the code groups for individual letters in a ciphertext, Emily can search for longer repeated strings of bits. These will represent common letter pairs called bigrams, letter triples called trigrams, or words. For example, any given 10-bit string should appear about once every 2 to the power 10, or 1024 times. If a 10-bit string appears 20 or more times out of 1024 strings, then it almost certainly represents the word the, which is by far the most common word in English. If you have identified the word the in a text, then you can look for extensions like there or these, which are easy to spot because of the repeated E. Mixed Huffman is rated 3.